Welcome back. Section 1-4 is on algebraic properties of matrix operations. Please expect one of the following proofs in your exams. Okay, that is, you will have to reproduce a proof, one of the proofs from this particular section in your exam. First algebraic property, addition is commutative. So matrix addition is commutative. That is, let A and B be two m by n matrices. Notice both have to be of the same dimension. Then A plus B equals B plus A. This is commutativity of addition. Here is a proof. Let A be the matrix Aij, m by n, and B be the matrix Bij, m by n. Then A plus B is matrix Aij plus matrix Bij, which is matrix Aij plus Bij. That is, individual terms have been added. But you see, addition is commutative in real or complex numbers. That is, Aij plus Bij is Bij plus Aij. So the matrix Aij plus Bij is equal to the matrix Bij plus Aij, which is matrix B plus matrix A. Hence, addition of matrices is commutative. This, starting from let until commutative full stop, is what is called a proof. You should be able to reproduce the proof using sentences, full stop marks, clearly stated explanation. Basically, we are saying matrix addition is commutative because addition is commutative in the real or complex numbers. That's the crux of your proof. Okay, starting from here until here, you should be able to reproduce if you are asked to prove that matrix addition is commutative. Okay. Likewise, matrix addition is associative. Let A, B, C be m by n matrices. They should all be of the same dimension. Then parenthesis A plus B plus C is A plus parenthesis B plus C. What this means is, you first A and B, add A and B, you get a result, add C to it. Compare that with first adding B and C and adding A to the left and checking whether the two sides are equal. Okay, here is the proof. Start with capital A, that is matrix Aij m by n. B, capital B, is matrix Bij m by n. And C, that is capital C, matrix Cij m by n. Then, what's the meaning of parenthesis A plus B plus C later? That is, parenthesis matrix Aij plus matrix Bij plus matrix Cij outside the parentheses. Well, matrix, the parentheses get computed first. So matrix Aij plus matrix Bij is matrix Aij plus Bij plus matrix Cij continues in the outside. Now, how do I add two matrices? Well, the first entry within parentheses plus the second matrices entry outside parentheses. But notice, these set of parentheses move away. So that becomes Aij inside plus parenthesis Bij plus Cij. So notice how the parenthesis within has moved away from Aij plus Bij and moved to Bij plus Cij. Okay. Why do we do this? Because addition is associative among real and complex numbers. That's why we can do that. Now we are able to separate, you see, we are able to separate these two to get matrix Bij plus Cij aside, matrix Aij on one end. This in turn is in parenthesis Bij plus Cij. Okay, that is capital A plus parenthesis B plus C. You see, parenthesis B plus C. So this is the proof of associativity of addition. All right. Now again, from let until here, you should be able to reproduce if your question were to prove that addition of matrices is associative. So make sure you can write this proof by hand repeatedly and reproduce it until you get it just right. Existence and uniqueness of additive identity. There is a unique m by n matrix O such that A plus O is A for any m by n matrix A. So you see, for every m by n matrix A, the same O should work. This matrix O is called the m by n zero matrix. Given any m by n matrix A, suppose we have a matrix U such that A is Aij m by n, U is matrix Uij m by n, and A plus U is A. Matrix Aij plus matrix Uij is matrix Aij. What does that mean? Aij plus Uij, its matrix is Aij. What does that mean? For every pair Aij, Aij plus Uij is Aij. And this has to happen for any Aij because that's what we are saying. Any matrix m by n, so any Aij. Well, among real and complex numbers, the only way this can happen is when every Uij is 0. Every Uij is 0. This happens because of existence of additive identity in real or complex numbers. That is, the matrix U has to be matrix of zeros. This is the existence and uniqueness of additive identity for addition of matrices. Okay, so we have proved starting from here to here, you should be able to write sentences, use symbols, complete with full stops at the end, and explanation to give a proof. Okay. Existence and uniqueness of additive inverse. For each m by n matrix A, there is a unique m by n matrix D such that A plus D is O. Remember O, the zero matrix. The unique matrix D is called the additive inverse of A and denoted by negative A. All right. A plus what is O, that what is negative A. Here is the proof. Let A equals matrix Aij m by n. Consider the m by n zero matrix O, that is the matrix consisting of zeros m by n. Let D equals matrix negative Aij. So whatever was Aij here, its opposite in here. Then A plus D is matrix Aij plus matrix negative Aij, that is matrix Aij plus negative Aij. Adding these two give you 0. So every Aij is 0. So the matrix itself is matrix O, which proves the theorem. Okay. Example, let matrix A be 3, negative 2, 4, 2, negative 1, and a complex number 3 plus 2i. This is okay, it's a matrix. This is a 2 by 3 matrix. There are 2 rows and 3 columns. Note the zero matrix. 2 rows with 3 columns is full of zeros here. That's the O matrix, zero matrix. Now check, A plus O matrix is your A matrix plus your O matrix. When you add individually, you're simply adding zeros, so you get A back. Okay. What about additive inverse of A? Additive inverse of A is negative A full of changed signs. Let's go back to A. Wherever you have negatives, become positive. Wherever you have positives, become negative. So remember, the middle column is negative. Middle column now is positive here. In negative A, everybody else is negative. So you see, even the complex number got negated. That's A. That's negative A. If I add them together, I get zeros everywhere. That's the O matrix. So negative A is indeed the additive inverse of A. Now here is a theorem. Multiplication is associative. Now you have matrices A, B, C of appropriate sizes. Why appropriate? Because you may not be able to multiply otherwise. You need the appropriate size to multiply matrices. Then A parenthesis BC is parenthesis ABC. Okay. Now this requires summation notation. Let A equals, that is capital AB matrix Aij, capital B be matrix Bjk. So notice I've used different variable Bjk. Why? I end at J, I start at J here. Likewise, C be matrix CKL. I ended B with K, so I started C with K. Okay, so I need to multiply. Look at their dimensions. Capital A is M by N, capital B is N by R. So whatever I ended with, I start with. Capital C is R by S. Whatever I ended here, I start with that. So now let's multiply A parenthesis BC. That is, BC is written within parenthesis. Matrix Aij parenthesis matrix Bjk matrix CKL. How do we multiply matrices using matrix summation notation? So notice the product is written in a matrix form, written in a matrix. Every entry, you see the common index K. K goes from 1 through R. K goes until R. K goes until R. So be mindful, these notations matter. Now how do I multiply this matrix with this matrix? Aij, you see the J? That J has to go from 1 to N. Why? Look at J. J goes until N. Look at J. J goes until N. So Aij parenthesis summation Bjk CKL. You see, two summations, they can be interchanged. So I kept the summation J out. I brought the summation K as well out. Kept Aij outside the parenthesis Bjk. Now matrix real number multiplication is associative. So you see the parenthesis here moved to Aij and Bjk. I have not changed anything else, only the parenthesis moved. Now I'll make one more change. You see the summations? Summations can be interchanged. So K going from 1 to R, here it's second, here it's first. J going from 1 to N, here it's first, here it's second. Why did we do this? See in a minute. You see J going from 1 to N applies to Aij, Bjk. CKL is irrelevant. Only these two. Correct? So I put that in parenthesis along with this and CKL outside. What does this mean? This means I'm taking this matrix, multiplying to the C matrix. That is AB and C outside. Okay. These two is matrix Aij, matrix Bjk. So this is a rather intricate proof. You will have to write it by hand 2-3 times to see the details carefully. I'll stop here, continue with the next video.